Okay, take 15. Right, earthships, 6 principles. Principle 2, solar and wind. Let's jump straight into that one. Solar and wind electricity. In terms of solar panels, they come in 2 types. So you've got PV, photovoltaic, and thermal. Solar photovoltaic is typically feeding a battery bank from the solar panel to store the electricity. Solar thermal is storing the energy in a hot water tank, warming the water up in that solar panel. Both of these panels are really common in Taiwan, so you'll see this one for electricity a lot, solar PV, and you'll see the solar thermal a lot on the roofs around here, houses and apartment blocks. I've seen some stuff in the last year or 3 combining, I think, PV and solar thermal, but let's just look at the 2 basics for the moment. So solar photovoltaic for electricity typically feeds a battery bank. A lot of people think you need really good sunlight to run solar PV cells, but you don't. In fact, they specifically design some now that work quite efficiently in cloudy conditions. Maybe not as efficiently as with bright sunlight, but they will work in sunny and cloudy conditions. And you'll see how few of these you might need for an eco home, an earthship, a straw bale home later in the presentation. The electricity storage with solar PV is typically in batteries, and some examples of those are lead acid car batteries. People worry about the lead, water contamination, pollution, ease of disposal when the life cycle of the battery is finished, but energy input, if you've got access to 20 old car batteries that aren't quite fit to run a starter motor in a car but can store energy for the home, is it worth reusing them? Another common type is lithium-ion, so these are in our phones, tablets, laptops, Tesla Powerwall. Again, life cycle of the battery, recycling them is a big problem. One of the things specifically is the battery itself is made up of layers of polymer with stuff in between it, electrolytes, anode, cathode, whatever it is. There's stuff in between lots of layers of polymer, so lots of layers of plastic stuck together, recycling that, pain in the, keep it clean, pain in the backside. So yeah, there's pros and cons to all of these. Nickel ion is one of the types that I hear mentioned a lot, spoken of as being one of the best in terms of the environment, because it's just nickel and iron, right? So yeah, what's it going to do? Rust. Probably don't want to drop it in your water tank, but I mean, to the other 2, lead and lithium ion, with lots of polymers in it, lots of sheets of polymer, possibly one of the best for the environment. It's got a couple of advantages as well that the other 2 don't have. You can repeatedly deep discharge nickel ion batteries, apparently. Absolutely run them right down and then recharge them, and they seem to be absolutely fine. You do that with your car battery, you're probably not going to start your car without battery again. You'll have to go and shell out $100 on another battery, or whatever they cost in your country. So they also take a lot of physical abuse and vibration as well, I think. So really useful batteries. Not sure how much they cost in terms of comparison with the other 2, but we can also use water as well as air, as well as something really heavy, mechanical, to store energy from solar panels, but we'll come back to that in a later slide. So solar thermal for hot water, stored in a hot water tank. Solar thermal panels can be placed on the roof with integrated tanks. This is really common in Taiwan to see this set up. They've got 6 right on top of the building next to me here. Sunlight hits that solar panel, the water's running through the pipes in the solar panel, the hot air rises into the tank above. There's your hot water for showers. You can also locate the solar panels on the ground outside the building, somewhere facing nearly southwest, whatever you can get, and then run the water pipes into a tank inside the building if you want as well. either, it's a really good way to get your hands on some energy from the sun to warm up your water for showers and baths. In terms of wind turbines, this is something that you'll typically see advertised, or when you look for wind turbines for your home, domestic wind turbines, that kind of thing. Typically, again, it feeds a battery bank. Each type of wind turbine has pros and cons when you start looking into them with regards to efficiency at different wind speeds, reliability, repair and maintenance, and cost of installation. You've probably seen some horizontal axis wind turbines like this, the big ones that feed the grid. There's a couple of YouTube videos that I've seen of one blowing up. The brake will fail in the gearbox, I think, is where the brake is located, somewhere in the top there, and you get a strong wind and then they just spin out of control. They need to spin, if you look at the blades on these, they're quite thin, really well designed aerodynamically, of course, but really thin, so you need wind speed to turn these. I think I've got a video in this presentation to show you, maybe after this. Yeah, so two basic types of wind turbine: your vertical axis wind turbine, left and right here. It's vertical axis, the axis that it spins around is vertical, it spins this way. The one in the middle is a horizontal axis wind turbine, so the axis is flat, is horizontal, and it spins around this way. And a Wikipedia link there as well if you want to get up to speed on some of the other stuff to do with wind turbines. I won't show you this video because this presentation is a Creative Commons share alike non-commercial. I haven't got their permission, but that video, you can get the link out of the presentation, have a look at it on their YouTube channel. Shows you a vertical axis wind turbine similar to this design here on the left, maybe made out of an old oil drum cut in half, welded together around a central axis. Maybe it uses a spare car wheel to transfer the energy from the turbine to the generator itself. But you can see the amount of surface area that you've got on those blades or sails, whatever you want to call them, on this wind turbine. It's a lot of surface area, so you need much less wind speed to generate rotation and generate electricity. Looks like a really torquey system, a system with a lot of torque. So you could probably turn a generator with some gearing at much higher speed than you can with these horizontal 3-blade designs here. But have a look at that video. This video here, that gives you some demonstration of a really slow wind speed, the horizontal axis wind turbine not spinning at all, and the drum kind of vertical axis wind turbine slowly spinning away. Okay, so other options to generate or store power here. This is pumped hydro with a micro turbine in our case. I mean, this looks like a rather large power station, but pumped hydro and micro turbine, if you throw those two phrases into Google, you'll get some joy. And you simply need a height difference between two water storages, a lower reservoir and an upper reservoir. Could be two ponds on your property. The amount of head is important. You'll see that in the literature or in the documentation when you start looking into this stuff, is the amount of head you've got. The higher the upper reservoir is in relation to the generator, the more power you can produce, the more electricity you can produce out of that generator. So it's a simple idea. If you're not using the electricity from your solar for charging your battery bank or running appliances or lighting, then you just use it to pump water from the lower reservoir to the upper reservoir in those times, and then you've got energy on tap, basically, waiting to go if you need to do anything really heavy and for some reason there's no charge in your battery bank or no solar available, no wind available. So that's fairly weather independent of weather, independent of the amount of sun that you're getting, and independent of the amount of wind you're getting. It's a nice option to have. Maybe not so good when you get up to Sweden, Norway kind of areas, but compressed air as well is something that you can use course, you're going to lose, there's loss in every system, but with compressed air, you're going to lose a lot of heat energy, lose a lot of energy through heat when you're compressing the air to put it in the tank. But I think I've seen stuff where you can fairly cost effectively get something like a gas tank from rail freight, from train freight cars, and use that to store your compressed air. So that's another way of doing it. You can do it mechanically as well, but yeah, you need something really heavy and a crane. I've seen people online do that. But so let's have a look at energy use. So if you're paying a lot of money for, the cost of solar has come down a lot now to where it's competitive with domestic prices for electricity produced with nuclear and coal and gas and so on. But the first rule would be to just use less, right? So if you're designing and building an eco home, it's a much more efficient home. It's going to need a lot less energy. These comparisons here are for kilowatt hours. So this is a typical medium-sized house in the UK. I've isolated the kilowatt hours for gas here because we mostly use gas for heating in the UK, sometimes for cooking, sometimes even for cooling. And electricity is generally used more for lighting and appliances, that kind of thing. So this is not perfect, but you'll see the figures for earthship annual heating and cooling are specifically for annual and cooling. So I'm trying to get us a ballpark comparison here. So 13,500 kilowatt hours is what a typical medium-sized house will use in the UK in terms of gas. Let's call it heating and cooling. And you can see there's a comparison here of annual heating and cooling loads in kilowatt hours for all the way from an earthship insulated burned greenhouse down to rammed earth. So a rammed earth building here is going to be very similar to an earthship uninsulated, right? Where are the figures? Yeah, just over 3,000, just over 2,600, just over 2,000. So all of these buildings, all of these eco home designs are way, way more efficient than your typical energy bill for a medium-sized house in the UK. And these figures are from 2014, we're 2019 now, just starting, so you're going to have a mix on the market between old stock and new stock in terms of the housing that these figures are taken from, I guess. But a lot of new housing in the UK is really efficient compared to the old stuff for heating bills in terms of the amount of insulation they put in them now. But still, you know, any kind of earthship design, any kind of straw bale design, cob design is going to knock the socks off it in terms of energy consumption. Colder climates, you definitely want insulation in the floors and so on. Warmer climates, maybe we want insulation depending on where we are. But you're looking at somewhere between 600 and, ignore that 3,000 there, sorry, 2,600 something. Yeah, 2,600, 3,000 is more for the rammed earth. When we compare those, it's fairly obvious looking at it on a chart, but if you're not really a graphs person, if this doesn't mean much to you, how much energy an earthship or eco home would use, we can do it in terms of solar panels as well. So if a regular house, that house we just looked at, a typical medium-sized house in the UK, if that needed 22 panels to heat and cool the home, then an earthship global model would only need one. A less efficient earthship, this type here, uninsulated, it's got no insulation, no berm, no greenhouse, and it still only uses a fifth roughly of the energy. A fifth to a quarter, what's that, 22, yeah, something like that. 5 panels compared to 22, that's no insulation, no earth bank, no berm at the back, no greenhouse on the front. So basically we need a lot less infrastructure, solar panels, cables, battery banks, to provide the energy required by the home. Again, these are guesstimates at this point, but I think it really illustrates the point. That's the end of solar and wind. Next time I think we're going to look at sewage treatment. So yeah, catch you at the next meeting.